So now that we've talked about how the design of the TimeMemoizer is going to be provided, let's talk about how to implement the TimeMemoizer by using the Java ScheduledExecutorService. And this particular implementation, as you may recall, uses this remove of stale runnable for every key value pair, and it uses it to essentially remove items, or maybe a better way to do it is to not reschedule them. It's probably a better way to put it. So they get removed if time passes and the key value pair has not been accessed within that time frame. So this is the class definition. You can see that TimedMemoizer implements the functional interface. We've done this before with Memoizer when we looked at that in earlier lessons. And this allows the TimeMemoizer to be used transparently whenever a function is expected. We then have ourselves a map field called mcache, which is of type concurrent hash map. We've talked about that a lot of times, so I'll kind of skip through that quickly. And this particular map, or hash map, concurrent hash map, is parameterized by key, which is passed in as the generic parameter to the TimeMemoizer class. And it's also parameterized by something called ref counted value. And we'll take a closer look at what ref counted value is in a second. And that's going to be used to keep track of the number of times a key value pair is referenced within the timeout period. We also, of course, have a field that keeps track of the timeout period, which is called mtimeout in milliseconds. And so it gives you a good indication of what the time unit is. We have a field that keeps track of the function that's registered to produce a value based on the key if it hasn't been produced before. We're going to keep ourselves an instance of ScheduledExecutorService, which is going to be used to execute these remove of stale runnables after their timeout elapses in order to check for and remove expired keys. And then we have this really interesting field called non-accessed value. And it's given a reference count of 1, and we use this to atomically check if a key has been accessed or not been accessed within the timeout period. And you'll see how this gets used. It's really super duper clever implementation that I'll look at with you in a moment. Here is the, here's the ref counted value class. This is the class that's used to record the number of times a key is referenced within m timeout milliseconds. Sorry. And you can see that this nested class has a couple of fields itself. It has an atomic long, which is the ref count, the reference count. And this is a value that's incremented atomically every time a key is accessed. So every time someone accesses a key value pair, that will be incremented by 1. And that's very important for use in determining whether an entry is stale or not, as you'll see in a moment. It's also, of course, got the value of type V. That's the value that's being reference counted by the reference count. It's got a constructor that takes a value and an initial count, and it creates a new atomic long to encapsulate that initial count and make into a ref count. And then it's got a get method. And the get method is pretty cool because what it does is it increments the reference count atomically, and then it returns the current value. So every time anybody accesses a key value pair in the time period, the elapsed time period, the get method is going to be called, and it will increment the reference count. And if you think about this for a second, what we're going to end up doing is when that remove of stale timeout goes off, then the timeout task is going to check to see if the reference count is greater than 1. If it is, it knows it was accessed, so it's not stale. If it's still equal to 1, then it knows it was not accessed in the time period and therefore is stale. And so there's 2 different arms of logic that we'll see used depending on whether a key value pair is deemed stale or not stale. We implement the equals method. Remember, equals is one of those methods that's inherited from Java object, which is the root of all classes and interfaces in Java, except for records, which came later. So equal in this particular case is going to be used by the concurrent hash map remove method to determine if the key has been accessed within the timeout period. And the way it does this is it checks to see if the reference counts are equal. And if they're equal, then that means that something is stale. If they are not equal, it means that someone has accessed the reference count and it has been incremented by 1 or more, and therefore it's not stale. And we'll see how that gets used in just a moment. Another key method, this is really the kind of the main workhorse method of the ref counted value class, is called schedule. And what schedule is going to do is it's going to take a key and it's going to go ahead and schedule a runnable that removes the key from the cache if it's stale. So let's take a look and see how this works. So this is what the runnable looks like, or this is what a portion of the runnable looks like. So we're going to make ourselves a new runnable. This is using an anonymous inner class for reasons I'll talk about in a moment. And this runnable is going to end up being scheduled with the scheduled executor service, and it will check to see if the cached entry becomes stale, and it'll remove it if so. So here's the run hook method. Now, keep in mind, this run hook method is going to be called back in the context of the thread that is the scheduled executor service thread. So the scheduled executor service, the thread that's running there in the background, is going to call this run hook method back when the timeout period elapses. We're going to schedule this runnable for a certain time in the future, let's say a second, just to be given an example. And when that second elapses, this run method will get automatically called back by the scheduled executor service in that background thread. Now, the reason why we're making this thing an anonymous inner class is because ultimately we're going to end up scheduling this object with the scheduled executor service. And because of that, because we're going to schedule it, we're going to schedule this, we have to use an anonymous inner class. We can't use a lambda expression because lambda expressions aren't objects, and therefore they don't have a this pointer or this reference, whereas the runnable anonymous inner class we're doing here does have that. And if you want to learn a bit more about this distinction between lambdas, which are not objects, and anonymous inner classes, which are objects, take a look at the link at the bottom of the slide. So when the run method gets called, the first thing it does is it goes and it checks the current reference count of this ref counted value object. And this logic here is ridiculously subtle. And the reason why it's so subtle is because we don't have a lock that locks the entire hash map or the entire logic here in our TimedMemoizer. Instead, we're using the super cool and highly scalable techniques that concurrent hash map provides. But because of that, we have to be very, very careful how we write the code. So we get the current reference count. And then what we do is we call the remove method on the concurrent hash map. And we pass in the key, which is the item that we're trying to see if we should remove. And we're passing in m non-accessed value. And the way that the remove method works is it's only going to remove this key if the value of m non-accessed value is equal to the current ref counted value. So the way to think about this is if this key value pair has not been accessed in the timeout period, in that particular case, it's considered stale and it has to be removed. So m non-accessed value is essentially a ref counted value that's given a ref count of 1. So if the ref count of that m non-accessed value is 1 and the ref count of this ref counted value is 1, that means that there's been no access within the time period. So in that case, it'll atomically remove the key. So that'll take it out of the map and we're basically done. We're not going to reschedule anything in that case. Otherwise, we're going to do some really, really cool fancy footwork with some of the features, the very powerful features that are part of Java's atomics package. And what we're going to do here is we're going to go ahead and try to atomically reset the ref count to 1 so it won't be considered accessed. And here's what we do. So we're going to call the get and update method, which atomically takes the current count. And if the current count is greater than the old count, in other words, if it's gone up since we took a look at the earlier version, since we cached it earlier, then we go ahead and set it to the current count. Otherwise, we set it back to 1. And if you come back up here, you can see we have old count up there. So if the current count of the ref count is greater than the old count, we make it the current count, because that means between the point where we read the value and the point where we're setting the value, somebody's come in concurrently and accessed that key value pair. And so the count has gone up. So this again is, really, really subtle, clever uses of atomics in Java in order to make sure we get the right count for this thing. And if nothing has changed in that intervening time, we just reset the count back to 1, which means that there needs to be some other changes later in order for this value not to be considered stale. The whole reason for doing this is we want to make sure that if something's accessed in this window of time, we count it as being accessed, and we don't ignore the fact it's accessed. So that way it won't get purged later because the count hadn't changed. And the reason why the ref count can be increased concurrently is the mcache concurrent hash map is never locked entirely because it's intentionally designed to be accessed concurrently. The last piece of the puzzle here is we take this object and then we reschedule it to run again in the timeout period or after the timeout period elapses. So if something was accessed during that timeout period, then we're going to say you're not stale. So we're going to go ahead and let you be rescheduled to run again in the future. And then the final thing that happens in the schedule method, what we've just been doing is looking at how the remove if stale runnable works. The final thing that happens in schedule is we go ahead and take that run if stale runnable that we just created and we schedule it to run at m timeout in milliseconds in the future. So that's where we are going to go ahead and register this thing the first time. And of course, henceforth, we may reschedule it to run if indeed this particular value is accessed in that time period. Okay, pretty darn cool, pretty darn subtle, and pretty darn efficient because of the way it uses all the features that are provided with concurrent hash map and Java atomics and scheduled executor service. So this is an indication of some pretty darn powerful concurrent programming code that actually took me a long time to figure out how to get it to work right. Let's now take a look at the constructor for TimeMemoizer. Its purpose, as always, is to initialize the fields in a TimeMemoizer object. You can see it stores the function and timeout parameters in local fields. It makes a new scheduled thread pool executor instance. This is a single-threaded version. We know it's single-threaded because it has a count of 1, so there's only 1 thread. We then go ahead and downcast this thing, and then we use the downcasted local variable to set the shutdown policies that remove scheduled runnables and disable tasks when things are shut down. And that was by design. Remember, I told you that the default settings for those policies are a little bit wacky. And so we want to set them to these values instead. All right, so that's basically how we create ref count values. That's how we initialize the TimeMemoizer. Now that you know all of that stuff, we can finally come in and look at the apply method. And the apply method is, of course, is the one that's going to be used to return a value that's associated with the key in the cache, potentially creating that value if it hasn't been initialized earlier. So let's take a look and see how this works. This is also very subtle, very powerful logic. So in this particular case, we're going to use the compute if absent method. Now, if you recall, when we had taken a look at the future task from previous lessons from last week, I showed you how to use the future task in order to be able to do this atomic check then act behavior. In this particular case, we're going to simplify things considerably, and we're going to use the compute if absent method, which is defined on concurrent hash map in Java 8 and beyond. And again, that's an atomic check then act method. What it does is if the key is already in the map with a certain value, we just return that value. Otherwise, we have to run this logic. So this lambda expression will otherwise be run, and this lambda expression will be run atomically, and this lambda expression will create, schedule, and return a new value. And that's what the code does here. So let's take a look and see how this works. We'll break it down step by step. So keep in mind, this lambda expression is being registered, and it'll be run when the timeout, or sorry, it's going to be run if there's not a value associated with the key. So the first thing we do is we're going to make ourselves a ref counted value, and that ref counted value will be initialized by calling the function to essentially give you the long running value. And again, keep in mind that this lambda that we're registering is not called at this point. This lambda expression is going to be called if somebody goes ahead and looks for a key that isn't yet in the map. So this function that'll be registered in that case is going to go ahead and apply the function, which for our case study would do prime number computations, but could be whatever. And it'll store that in the map initially with a ref counted value of 0. Oh, sorry, it creates a ref counted value with a value of 0. So this apply method runs in the thread of control of the method that calls apply. And then what happens here is we're going to schedule this object by calling the schedule method on the ref counted value. And that's going to go ahead and set things up with that remove if stale runnable we looked at a little while ago to run in the future. The thing to note about this particular implementation, which we will fix later, is that a runnable is created for each key value pair that is passed to scheduled executor service. And then we return the ref counted value. That's what gets returned from this particular call when it runs. And then we go ahead and say ref counted value.get. And what that's going to do is that's going to go ahead and atomically increment the reference count and return that value. So that's the end of the implementation here that uses the run if stale model of associating or scheduling a runnable task to run to determine whether an object has become stale or not.